This is the second lecture for Chapter 12, which deals with alkanes. In today's presentation, we will cover the following: cycloalkanes. So we'll look at that and define it and look at some examples. We'll also look at a concept called cis and trans isomers of cycloalkanes. Next, we will examine line angle representations of cycloalkanes. And we'll also look at the physical properties of cycloalkanes. And lastly, we'll look at two reactions that alkanes undergo, which are basically oxidation and halogenation. So let's begin. Cycloalkanes are basically cyclic hydrocarbons. Notice hydrocarbons contains hydrogens and carbons. The main difference here between the compounds that we have discussed in the first part of the chapter is that they are joined by a ring. So look out for that ring. Cycloalkanes contains carbons that have 4 bonds to it. 4 single bonds. Keyword here, 4 single bonds. So let's look at this one. This is a cycloalkane. It has 1, 2, 3, and 4 carbons. We know from the first part of this chapter that if it contains 4 carbons, it's a butane. Since it's in the form of a ring, it's a cyclobutane. Notice we can write it like this, which is the line angle. Remember that here is a CH2 because there are 4 bonds to each carbon, and at each intersection or angle there's a carbon. Let's look at this one. This has 1, 2, 3, 4, and 5 carbons. Make sure you check the carbons because that determines the name. 5 carbons would be pentane. Since it's in the form of a ring, it's a cyclopentane. Here is another way of drawing this, and that's called the line angle representation. Again, right here is a CH2, 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 and a CH2. This is not surprising if you were asked to name that molecule. It has 1, 2, 3, 4, 5, and 6 carbons, making it a hexane. And since it's in a ring, it's cyclohexane. So this table gives a summary of the cycloalkanes. 3 carbons would be a cyclopropane, etc., etc. 7 carbons would be a cycloheptane, and 8 carbons would be a cyclooctane. So you have this table available whenever you are taking a quiz or an exam. Let us look now at the nomenclature of substituted cycloalkanes. Substituted. So now we have the cycloalkane, but now we'll have a group bonded to that ring. We call that a substituted cycloalkane. How do we name that? Just as we did before, you have to recognize the cycloalkane portion, and you'll have to name each substituent on the ring. So, let us look at some examples, a couple examples. Here is one. This is a cycloalkane right here. Why is it a cycloalkane? Because here is the ring and here is the substituent. So how do we name that? You have to identify the ring. Here's the ring. So it's 1, 2, 3, 4, 5, and 6. Well, 1, 2, 3, 4, 5, and 6. So it is now a hexane. It's in the form of a ring, so it's a cyclohexane. It has a methyl group here, methyl. Why methyl? Because it just has one carbon. One carbon corresponds to methane, but since it's a substituent, it becomes methyl. So here is the methyl cyclohexane. It's on carbon number 1. We have to start numbering at the branch, so we could put a 1 here, but it's usually not used. Here's another example over here. This is a 5-membered ring. 1, 2, 3, 4, 5-membered ring. So it's a pentane. Since it's a ring, it's a cyclopentane. On the ring is bonded a chlorine, and the chlorine becomes a chloro, so it becomes chlorocyclopentane, and the 1 can be used here again, but it's typically not used because it's understood. Let us look at a more complex molecule. This one has 2 substituents. So if we have 2 substituents, what do? First, we have to number the ring, and we have to start at the point where the substituent is, and based on the alphabet. So in other words, we have to start based on the alphabet of the substituent. So let's look at this. So here's the ring right here. 1, 2, 3, 4, 5, 6. So that becomes a cyclohexane. Here's the cyclohexane portion right here. And we have a methyl. And we have a methyl bonded to this cyclic system. So we'll have to indicate the methyls, and we'll have to indicate here their location based on the number. Since we have 2 methyls, we can say it's a dimethyl, and they are in positions number 1 and 3, and here's the 1 and here's the 3. Notice that the 1 and the 3 are separated by a comma, and there is a dash between the 3 and the letter D. So let's apply that over here. This is a 5-membered ring. 1, 2, 3, 4, 5. So it becomes a cyclopentane. Make sure you don't get them mixed up. 5 would be pentane, so it's a cyclopentane. Right here is the cyclopentane portion, which is right here. Okay, we could number going 1, 2, 3, 4, 5, or as shown here, 1, 2, 3, 4, and 5. Notice we start numbering at C. This is chloro, because C comes before M, and this is a methyl. So since C comes before M, this gets number 1. And we go in the direction of the branch. So we do not go away from the branch, but in the direction of the branch. So that is why the numbering goes in this direction and not the opposite. With that done, we now have 1 chloro and 3 methyl. Notice C comes before M, so that's why we list the chloro first and the methyl next. It may sound complicated, but it's just a matter of applying the rules here. That's called the IUPAC rules for nomenclature. Let's go on. Now let's look at isomers. So we're going to look now at isomers of cycloalkanes. Remember, it's a cyclic structure, so we cannot have a cyclic structure if it's 2 carbons. But once we have 3 carbons, cyclopropane, it's possible to have isomers if we have substituents bonded to it. So let's go. So here is cyclopropane, 1 and 2. Notice we have to go in that direction, and this is carbon number 3 because we go in the direction of the branch. So here is our cyclopropane right here. We have a methyl on carbon 1, and we have a methyl on carbon 2. So that means we have 1,2-dimethyl cyclopropane. Since the cyclopropane ring here is a rigid structure, as you can imagine, a triangle, so we can have the methyl group on one side of that triangle and the other methyl group on the opposite sides. So these groups here are on opposite sides. That means they are trans. So the term we use is trans and not opposite. So we say that the name of this molecule is trans 1,2-dimethyl cyclopropane. Let's go over here. Looks like it's an isomer. Why an isomer? Because it has the same molecular formula. It's just that the arrangement of the groups are different. So here we go again. 1, 2. Notice we're going in the direction of the substituents, and 3. So again, it's a cyclopropane. We have a methyl group and a methyl group. This time they're on the same side. So instead of saying same side, we say they are cis. So it's cis 1,2-dimethyl cyclopropane is the name of this molecule. They are isomers because the arrangement of the groups are different. They have the same molecular formula, but the arrangement of the groups are different. One is a cis isomer, and the other one is a trans isomer. As you've seen in chemistry, we have different ways of writing, of communicating. So here's a different way of communicating the trans isomer. You may recall we did the dashed wedge, where the wedge here, here's a wedge, that means front, and here is the dash, that means it's in the back. So you can see here, this group is in front on this carbon, and this group is in the back. So therefore, it's a trans relationship. So you can use the dashed wedge representation to write the isomers of cyclic compounds, or you can use the line angle. Here's another representation of the cis. So here's this carbon. This group is in the back, and this methyl group is also in the back, which means that they are on the same side. Instead of using the word same side or the words same side, we say they are cis. The relationship is cis, and of course we have 1,2-dimethyl cyclopropane as we had before. Here's another example. So here this is a cyclobutane. Let's see, why is it a cyclobutane? 1, 2, 3, 4. And it's in a ring, so therefore it's a cyclobutane. There are two groups, a methyl here and a methyl here. They are on position number 1 and on position number 3 of the ring, so therefore it's a 1,3 dimethyl. Notice this di here represents these two. And of course methyl, because it's only one carbon and one carbon here. It's cis because they are on the same side. Okay, another way of writing it, as we've said here, here is a wedge, which means in front. And here is a wedge, which means front. So therefore, same side, so therefore, cis. So we have two ways of writing the structure of cis 1,3-dimethyl butane. Let's look at other molecules. Here is, we have the cyclopentane. So we have here 1, 2, 3, 4, 5, but we won't start numbering there because there's not a branch. We have to start numbering where there is a branch. So this becomes 1. And we have to go in the direction of the branch. 2, 3, 4, and 5. So that's a cyclopentane. Two methyl groups on carbons 1 and 2, so dimethyl, same side, so it's a cis. This is the trans because we have them on opposite sides of the ring. Here is a ring. So one is above and one is below. So look out for that. What you should be able to do also, if given the name without the structure, can you draw the structure of this molecule? We'll give you an example in a second. Here is another representation of the cyclopentane. So we have here 1, 2, 3, 4, and 5. Cyclopentane, cis, dimethyl, because we have a methyl group on carbon 1 and a methyl group on carbon 2, and they are on the same side, so it's a cis. This is a trans because they are on opposite sides based on this dash means in the back and this wedge means in the front. As you've seen, as you can tell here in chemistry, we use a lot of symbols to communicate, a lot of symbols, and it's just a matter of understanding what these symbols mean. So make sure you understand the meaning of these symbols because we will communicate using these symbols. Let's look here at the six-membered. I think this is the last one we'll look at as an example. So let's look at the six-membered ring. This is not surprising. This is a trans because we have here the dimethyl and the methyl on opposite sides. But let's work it through. So let's work our numbers. We start numbering at a branch. So here's 1, 2, 3, 4, 5, and 6. So on carbon 1, there's a methyl group, and on carbon 4, there's a methyl group. So it's 1,4-dimethyl cyclohexane. Why cyclohexane? Because this is a ring. Why trans? Because one methyl group is below the ring and the other methyl group is above the ring. This is another way of writing the same molecule. Notice it's the same molecule, but just written using a different format. This is in the back and this is in the front of the ring, so they are on opposite sides, so therefore it's a trans. As you can imagine, this is a cis. 1, 2, 3, 4, 5, and 6. So it's a 1,4-dimethyl cyclohexane because it's a ring. Why 1,4? Because we have a methyl group and another methyl group on carbons 1 and 4, and they are cis because they are on the same side. Same here, in the back and in the back, same side. So therefore, it's a cis 1,4-dimethyl cyclohexane. Okay, let's apply what we have just learned. So here are a couple of questions which are similar to what you will see on the quiz and on the exam. So the question is, give the IUPAC name for the following molecule. Notice it says here include cis and trans if applicable. So in other words, what we're asking you here is, did you understand the concept of naming cyclic compounds? If you did understand the concept of naming cyclic compounds, let us apply that concept here. So here's a molecule. What is the IUPAC name? The other question is, give the structure if given the name. Here's the name. Trans 1-ethyl-3-methyl cyclohexane. Can you give the structure down here? So this becomes really the meat or the aspect of chemistry, especially organic chemistry. It's not a course you can memorize your way through it, but it's a course you'll have to know the concepts. But equally important, you'll have to apply these concepts to solving problems. Here's a problem. So you'll have to have a systematic way of solving it. So let's see if we can come up with a systematic way first, and then we'll look at the answer on the next slide. So here we have the cyclic system right here. Hope you can recognize that. And that's 5 carbons. So we know that's a cyclopentane. We got to start numbering by putting 1 either at this carbon or at this carbon. But first, let us look at the substituents bonding here. This is a substituent with 2 carbons. So that's an ethyl from ethane. And this is 1 carbon, which is methyl. So therefore, since E comes before M, we're going to put 1 right here. The question is this number 2 or is this number 2? We go in the direction of the branch, so this is 2, and 3, and 4, and 5. So now all you have to do is put these together to come up with the name. So you can see it's going to be cyclopentane, and it's going to be 1 ethyl and 2 methyl. We'll see it in the next slide. Let's look at how we'll solve the structure here. My suggestion for writing the structure is start by looking at the end, the ending, cyclohexane. So you may want to draw here a 6-membered ring. You have a choice here. You can put 1 anywhere. So let's put it here. So this would be 1, 2, 3, 4, 5, and 6. But now that you've labeled it like that, on carbon number 1, we'll have to put here the ethyl, 2 carbons. And in carbon number 3, you'll have to put the methyl, CH3. It says trans. So at some point you have to indicate 1 being up and 1 being down, opposite. Okay? So let us see what's the answer. By the way, I didn't point out, but notice the stereochemistry here, or the cis-trans chemistry here, they are on the same side. So this and this are on the same side, so it has to be cis. Let's see what's the answer. So what we have here is, how do we name this? So we go 1, 2, 3, 4, 5, 6 as we did before. Here's the ethyl, here's the methyl, and the relationship is on the same side. Which makes it a cis. So the name would be cyclopentane because we have a cyclopentane ring. And we have here 1 ethyl, 2 carbons, 1 ethyl, and 2 methyl, and cis because they're on the same side. Notice again we have a dash between letter and number. And if we had 2 numbers, we'd put a comma. Okay, what's the structure of this? I suggest start here with the cyclohexane. So here's our cyclohexane ring, right here. And of course, we started number 1 here. So number 1 would be the ethyl. So here's the ethyl group, 2 carbons. And of course, we have methyl on number 3, 1 carbon. And trans is an important aspect because we have here, this is a dash and this is a wedge, which means opposite sides. So therefore, that's our trans. So this would be the structure. Okay, let's go back so you can really see it. So this would be our structure here for this molecule, and this would be the name here for this molecule. Okay, so you should be able to come up with a name given the structure, and the structure given the IUPAC name. Let us look at some physical properties. Remember, physical properties here by definition is any observable or measurable property of a compound in any aspect or characteristics that are measurable and observable. The boiling point, for example, is a physical property because you can measure the boiling point of the alkanes. The color is an observable characteristics. So let us look here at the electronegativity or polarity. The question is, are alkanes polar molecules or non-polar molecules? Just to give you an example of a polar molecule, we have here HF. That's a polar molecule because, as you know, F is very electronegative and it's bonded to H, which is not electronegative. So this is a polar molecule. CH4, on the other hand, is non-polar because, as we can see here, the electronegativity of hydrogen and carbon, they are about the same, pretty much the same, equal. So therefore this is non-polar. So alkanes or hydrocarbons are non-polar molecules compared to water, which of course, as you know, is a polar molecule. Let us look now at aspects such as melting points and boiling points. Let's first concentrate on boiling point. As you know, for a liquid to boil, the molecules are attracted to each other by intermolecular forces. We have intermolecular attractions between molecules. The intermolecular attractions between the fairly non-polar hydrocarbons or alkanes are called London dispersion forces or van der Waals. They're very weak. So that's why the boiling points of alkanes are very low. As you know, most of them, a lot of them exist as a gas at room temperature. But of course, as the molecular weight increases, as you can see here, as the molecular weight of the hydrocarbon increases, so does the boiling point. So you'd expect methane to have a lower boiling point than propane, and propane to have a lower boiling point than a hydrocarbon that has 8 carbons, which is octane, for example. Let us look now at isomers of an alkane. So here is an alkane, C6H14, 6 carbons and 14 hydrogens. There are different isomers with the same molecular formula. Different isomers. Remember, isomers here have the same molecular formula, but just the bond-to-bond connectivity is different. So let's look at this isomer, hexane, straight chain. Its boiling point is 68.7. Pretty high. Let's look at another isomer of the same molecule, C6H14. Now it's 2,2-dimethylbutane. You may want to draw that structure so you can see the difference. Notice here the boiling point now is 49.7, almost 50. So it's less than this one. Why is it? And they have the same molecular formula, same molecular weight. What you'll have to do is look at the structure. Hexane is pretty long, as you can see here. Lots of what we call surface area, pretty large surface area, which means that the attraction between this molecule and another molecule just like it, there is going to be attraction between both using the van der Waals or the London forces. To boil a liquid, you have to break these attractions. Let's look at 2,2-dimethyl. It's very compact, as you can see. So there is a smaller surface area. So if you have another molecule just like it over here, there is not as much an attraction between another molecule, or the intermolecular attraction is much weaker. So therefore the boiling point is lower than that of hexane, which has a larger surface area. Conclusion: isomers that have larger surface areas tend to have higher boiling point compared to isomers that have smaller surface areas. I think I have another example here. So let's look at this one. This is C5H10. And here are 3 isomers of C5H10. Pentane here has larger surface area compared to 2,2-dimethylpropane, which has a smaller surface area. So that's why you would predict the boiling point of this molecule here is lower than that of this molecule here, pentane, which has a larger surface area, which as you can see is 36 degrees C compared to 4.4 degrees C. So you should be able to predict the boiling points, or the relative boiling points. You need not know the exact number, but the relative boiling points of isomers based on looking at this structure. Let us look here at another property, the solubility. So, as we said, don't forget, you've learned this in Gen Chem, like dissolves like. That means a polar molecule will dissolve a polar solute. That's why sodium chloride, which is very polar, will dissolve in water, which is very polar. However, since hydrocarbons are non-polar, they are not soluble in water. So not soluble in water because they are not polar molecules, hydrocarbons that is, and water is a polar molecule. That's why we said like dissolves like. As you can imagine, hydrocarbons will be soluble in hydrocarbons. So alkanes are soluble in each other. So we can say that octane is very soluble in pentane, for example. The density. Of course, as you know, the density is a measure of the mass per unit volume. Alkanes tend to have density less than 1. So alkanes have densities that are less than 1. Why are we using 1? Because water, as a reference point, has a density of 1. So as you will recall, if you mix two liquids of different densities, the less dense would be on top. And the more dense, the heavier one, would be at the bottom. So therefore, if we mix two liquids, and hydrocarbon and water, the hydrocarbon would be on top. So that is why when you mix oil and water, the oil is on top compared to the water, which is on bottom, because water is more dense than hydrocarbons. Okay, let's turn our attention now to the reactions of alkanes. We have two reaction types. One is oxidation. So let's start with oxidation. Oxidation is pretty simple, which we have done in Gen Chem. It's just the reaction of hydrocarbons with oxygen. So we'll call it oxidation. Some books call it combustion. The main benefit here is that the reaction of hydrocarbons, alkanes, with oxygen is that it liberates heat. In addition to carbon dioxide and water. As you know, methane is a natural gas and used to heat different aspects or to cook, and it gives off heat. Propane is another one we can buy at the hardware store to use in the grill. As you can see here, propane gives off even more heat per mole of propane, but it's the reaction with oxygen and oxidation or a combustion to give carbon dioxide and water. Another type reaction is the reaction with halogen. We'll call that halogenation. So let's look at this. This reaction is called a substitution reaction. As you can imagine, substitution here means taking one atom and putting on another atom in its place. So here's methane that you're familiar with, CH4. So just imagine here is one hydrogen. The reaction with chlorine in the presence of heat or light gives us a substitution reaction where we're substituting this hydrogen for a chlorine. So we have a product of chloromethane. The other product, as you can imagine, is this hydrogen will bond with one of these chlorines to give HCl. So once again, it's a substitution reaction where one hydrogen is replaced with chlorine. So that's the concept. For this type reaction, it's taking only one hydrogen and substituting a chlorine for that hydrogen in the presence of heat or light, and of course using chlorine as a reagent. So let us apply that here. So here we have ethane. If you're asked to predict the product of the reaction of ethane with chlorine in the presence of heat or light, what would be the product? You take off one of these hydrogens and put on a chlorine to get this type molecule, chloroethane. Written differently here, here's cyclohexane. Notice the hydrogens are not shown. As I mentioned earlier, we have different ways to communicate the structures and concepts in organic chemistry. This is the line angle structure here for cyclohexane. The hydrogens are not written, but of course you know right here we have two hydrogens. One is right here and one is right here. They're not written in, but you know they are there. Here's chlorine, same chlorine as this. Here's heat, the energy that's supplied. So what is the product? You take one of these hydrogens and you substitute chlorine. Of course, the other product is HCl. So this becomes the product. for the quiz and the test, you should be able to predict the products of the halogenation substitution reaction. Let's look at a couple more examples before we quit. Here is the line angle representation of propane. So if you're asked to predict the product of the substitution reaction, here are two hydrogens. So taking one off, we could have a product here. Here are three hydrogens, CH3. Taking off one, we could produce that. So we have two possible products. We call this mono-substituted because we're substituting just one hydrogen for a chlorine. Let's look at this one, butane, line angle for butane. CH3 right here, CH2, CH2, CH3. We have chlorine in the presence of heat, so we need to substitute one hydrogen for a chlorine. You could do it here because this is CH3 right here. So you could substitute one of these hydrogens for chlorine, and here it is. I just got it switched around. So just not to confuse you, here's the same thing. One hydrogen for a chlorine. We have here two hydrogens, 1, 2. One of these hydrogens for a chlorine, so we have two possible products, and of course HCl as another product. Okay, let us look here, we just conclude here, let us look at some practical aspects of halogenated hydrocarbons. So we have here chlorofluorocarbons, known as CFCs. Years ago, they were manufactured under the name Freon. The moment I mention Freon, you may get the connection that they're used in refrigeration units and in air conditioned units, used as solvents sometimes. However, as we'll see in the next slide, they present a problem to the atmosphere. So they cause problem by destroying the ozone layer. So these chlorofluorocarbons are destructive to the ozone layer. Of course, as you know, the ozone is used to protect us from UV light. So they were banned a few years ago. They have been replaced by hydrofluorocarbons, HFCs. The aspect here is that they are a little more reactive, so they get destroyed before they get up to the ozone, the stratosphere where the ozone layer is, so it's not as destructive to the ozone layer. So now we'll find HFCs instead of CFCs in our refrigeration units. So here's an example. You need not know the structure of these. These are just for your information. And see, I think this is the end of the chapter. So again, this is the last lecture for chapter 11. So don't forget, we have a quiz on Thursday, this Thursday, which is February, what's that, the 3rd. And of course, we have our exam the following Thursday, which is the 11th. So get prepared for that. Review this material. Again, I'll post this on YouTube, and I'll also post the PowerPoints on D2L, so you can take your time and go through these lectures. And don't forget, have your book right there beside you as you read, and stop the video and work some problems. Okay? So continue to study hard, and I'll post this before too long.